to say is that we'll have discussion this week, starting tomorrow. Yeah, please stay up with the reading. Keep emphasizing that the lectures are just a supplement, not just. It's actually quite a bit of work, but it's a supplement to the reading as well. Vice versa, the reading is a supplement to the lectures, and for most part, the lectures fill in the gaps. Maybe emphasize some areas which are troublesome for the students, at least in the past, is what I've seen. So I won't exactly cover things in the text. I will parallel it. No question. I thought I heard a question. Maybe not.
If someone just might not be muted.
What's that?
Someone might just not be muted.
Oh, okay. Yeah.
Should we expect anything other than Gauss's law for the quiz tomorrow? Should we be studying anything else?
Yeah, I guess Gauss is a possibility. Maybe some of the material that we covered today on, potential energy, potential, definitely, flux or, Gauss's law is something as a candidate, no doubt.
Thank you.
Mm-hmm. All right, so our travels in this course so far has taken us to the land of electric charge, and we have explored basically how electric charges interact with each other, at least in terms of forces. And now what we want to do is we want to turn our attention to these interactions in terms of the energies, or for each charge, there's like associated these basically are directly related to that of forces. Talk a little bit about that at the beginning. At least I want to talk about initially, comparing this, to the mechanical world. Of course, as you guys probably remember, it's work done on the object that basically transfers the energy from one object to another, or you can say that it transforms the type of energy going from potential to kinetic and vice versa. Catalyst, I guess, is a better word of describing it. But in a lot of cases, work done is equivalent to potential energy, especially if you're maintaining a static equilibrium. And, you guys, I remember from 207, Newton's law for gravity. Hello? Anyhow, Coulomb's law and gravitational law, those two are really mathematically equivalent. And general features discussed, physics 207. The first part of this mechanical side of this full course will directly apply to electrostatic forces in a lot of ways. As you can see here in this diagram, that we have a electric field. Remember, electric fields move from positive charges to negative charges, and basically what's going on here is that you have work done on the this electric charge. This is work done by the field, and you can see the motion will be to the right. In that case, there'll be positive work, at least positive work done by the field. Okay, and we'll talk a little bit of differences between that, actions directly on the object versus the field work done. And this is equivalent, in the potential energy of gravity. As the object rolls downhill, well, the direction of the force and the direction of the motion, in this case, they're in the same direction for the most part. At least, the dot product between the motion of the object and the direction of the gravitational force is positive. In this case, there's a projection downward, and basically, that gives us the work done by a gravity field. So, oh geez, I forgot to bring something with me, but sort of just kind of go over this a bit. I mean, you guys, probably all you remember like work done by gravity versus that by a person that's moving an object. But you know, for instance, here I have this hand sanitizer bottle. I don't know if you guys can see me on the other screen. There should be another screen. And, on the other side, you see a chalkboard?
Yeah, we can see it.
Yes?
Yep.
Well, you know, this case here, you know, I have a small bottle of hand sanitizer.
Oh no, your camera is facing like toward your chair, not a chalkboard.
Yeah, I don't know.
Yeah, there's a
it's supposed to
second
be-
camera. Scroll down.
Is a second account on here?
There's
Sorry?
a camera.
Maybe I should just go over here in the unshare screen. I'm not really sure if you guys can see me or not. I'm going to unshare, so hopefully then you can.
Chalkboard. We can see you. There's just 2 cameras for you.
Yeah, I did have two laptops. One is facing toward a chalkboard, the other one is facing toward me.
We can
Can you see me now?
Yeah, we can see both of them.
Okay. All right, well, then I can switch back to the configuration I had. Just getting back in describing you know, work done by a force, gravity field in this case. You know, when I toss this hand sanitizer bottle upward, of course, reaches some apex and comes back in its trajectory. But on the way up, the motion is upward, but the force acting on it, gravity, is downward. And so this, you know, F dot dr, F dot dx, in this case, that dot product is negative. So we're doing, at least the gravity field is doing negative work on the object. And usually the case, I mean, if it's dynamic like it is in this case here, that the gravity field, when you do negative work, you're converting kinetic energy to potential energy. Okay. Now, in a situation where it reaches the top of its trajectory and returns back to me, it turns around. Now its motion is downward in the same direction of the force of gravity. Dot product between those two, a positive, so we're doing positive work. So typically in this situation, doing positive work, at least by field, you're converting potential energy into kinetic energy. So it's just a reminder, you guys probably know all this. I thought it'd be a good idea to just repeat it. But here's another thing too. Now, it's hard to probably see this. I'm gonna use a book, a little easier to see this book. Let's say I'm holding this book, and actually I'm fighting against gravity from it moving. I'm doing no work right now, although it feels like I'm doing work, but it's not moving. So no work is being done. Force of gravity is downward, and my hand acting on the object is upward. Now, if I move it upward, I'm applying a force in the upward direction. So I'm doing positive work because the motion and the force acting by my hand, it's all in the same direction. But the gravity field is doing negative work, right? Because gravity is downward and the motion is upward. So while the gravity field is doing, in this case, negative work, I'm doing positive work. And they're the same. Basically, it's the magnitude is the same. It's just one is opposite than the other in terms of a negative sign and polarity. I just wanted to make that point that here I'm doing negative work. I'm doing positive work on the book. Now I'm doing negative work, right? Because the motion's downward, my force acting on the book is still in the upward direction. I'm still holding it. I can feel it. But the motion now is downward. The force is upward. So now when I bring it down, I'm doing negative work, but the gravity field is doing positive work. I don't know if that, you guys probably remember all this. I don't know, but it's just getting the signs right. It's important in this. So I'll try to reshare. So negative work, at least by a field, in this case in a gravity field, as I was just illustrating earlier, it increases the potential energy. And positive work by a field decreases the potential energy. But on the other hand, my hand, as a matter of fact, when I was holding the book in place, it was the opposite of that. Right? When I was applying positive work to the book, I was in fact, I was doing positive work in this case. All right, let's try to do a little example here with a point charge. All right, so imagine I do have a point charge Q, say Q1, and I have another. So I have an observation point here, an observation point, another charge. I'll call it charge 2. And it's just pretty clear that if I were to bring this charge in from infinity, I mean it's kind of exaggeration to do that, but let's say I'm a Trabant, this charge, and I'm bringing it over into Sharp Lab. You say Trabant is about an infinite distance away for most comparisons here, considering this length here is about maybe 5 centimeters, well, maybe more, 5. So I'm having to do work on this. I'm having to do work on the charge to bring it closer to Q1. It's like a spring, you can think of it that way. It gets harder and harder as I get closer because of the 1 over r squared effect. If they were connected to say a little string, if I cut the string, then they would just rapidly move away from each other in this case. So all right, so I would basically just kind of work in this a little more detail. So let's say we move the charge back. This is not quite an infinity, but this is where we're starting. And say I am applying a force to move it toward point P. So this is me. Okay, but the electric static force is in the opposite direction. And so as it gets closer and closer, I have to work harder and harder to displace that charge to that location. And this is the work that I have to do here, right? Remember the force, in this case, it's in the same direction of the displacement. And I started at infinity, and then I moved it in a distance r away from Q1. And this is equivalent, one and the same, is writing this in the following way. If we start at r and move Q2 out to infinity in terms of the field acting on this charge, you should get the identical result. So force is opposite, but it's equal in magnitude. I mean, this comes about from Newton's third law of motion. So it's a little bit easier. I mean, I know the force, electrostatic force. I don't know my force exactly, precisely. I mean, one just from the arguments, you say, well, it has to be the electrostatic. But this is a little more known, so I will just include, it's using coulombs in this case.
Professor?
Yeah.
What is JC?
That's my initials.
John Clem.
Gotcha. Thanks.
Yeah.
Professor, can you just like re-explain again why
Yeah, actually, I just realized an error that we have here, but
Shouldn't that R be an R squared on the
yeah,
denominator?
exactly. But thank you. I'm glad you guys are pay attention to my mistakes. That should be an R squared. It's just on the next step when I integrate this, it becomes 1 over R. But I'm sorry, there was another question before that.
Yeah, I just was wondering if you could re-explain a little bit why infinity is an integration bound here.
Well, yeah, because we know that's where the force is 0. This is how it's defined as 0 is at infinity.
Oh, okay. All right, I see.
Yeah. So that's our reference point. I mean, we could do like a point to point, and then we would have like a differential or a work difference in this case. But just starting on infinity makes it a clean upper limit or lower limit for 0. And I got to change this to R squared. Everybody sees that this should be R squared because that's electrostatic force, coulombs. So when I integrate this, this doesn't become a log. That's what it would be if this was correct, but it's not. So the integram becomes minus 1 over R. And this is basically, you can think of work done. But it's also the potential energy, at least in the static case, where we're not allowing objects to move freely. Unlike the hand sanitizer bottle, it's held in a static situation. It's in some equilibrium. Maybe at one point it was in motion. Of course, it was motion when I was integrating from infinity to point P. But once we reach there, it's static in that case. And we're not converting anything from potential to kinetic or kinetic to potential. It's stationary. And so the potential energy, just like that in the case in the mechanical world, for the gravitational fields, the units are in joules, just like kinetic energy would be in joules. This is the SI unit. So I need to correct this to be R squared. There's another point here. It says, if Q1 and Q2 are positive, I do positive work since the charges repel. They repel themselves. So I have to push and push to do positive work to bring these two together. And if they were unlike, I would do unlike me, like if Q1 was negative and Q2 was positive. In that situation, I would do negative work. In some sense, what I'm doing is I'm pulling on the charge to keep it from accelerating toward Q1. So my force actually is in the opposite direction of motion. So in that situation, I would be doing a negative work. However, in that situation, say if the charges are unlike, the electric static field would be doing positive work. You guys see that? The charges attract each other. Q1 wants to accelerate toward Q1. Q2 wants to accelerate toward Q1, and so basically the force is toward the right. Toward the left. The force acting on Q2 is toward Q1, which is to the left. And the motion is to the left. And since those two forces are parallel, the cosine theta is positive. And so you're doing at least the field is doing positive work. Remember, if we were to just let go of that charge, the work done on Q2 would be converted to kinetic energy. In a conservative system like this, kinetic, the total kinetic and potential energy, that total mechanical energy is conserved. Now, in this case, we just went, it's like a straight line. We took a straight line, from all the way from infinity to the point P. But do we necessarily have to do that in a conservative force? field, such as this one? Is it necessary to take a straight line? I mean, would I get a different result if I were to take a curved path?
No, because it only matters the starting and ending points.
Yeah, it's right. It's one of the definitions of a conservative force is that calculating the work done is path independent. In other words, friction or any dissipated forces or drag, such as velocity dependent forces, are not present. So you're always able to recover the energy, from the kinetic energy back to potential. And regardless, I had a little fun here. Regardless of our path, maybe a little too much fun, that you would end up with the same potential energy. That would not change. I mean, I hope you're convinced of that. You guys have seen this, I assume, in 207, right?
Yeah.
Yeah, we've seen that.
Yeah. All right. So it's the same amount of work as we would if we were to take a straight path. It's easier to draw straight paths. So now, the total amount of work to assemble, a charge distribution, a distribution of charges, is just the sum of the work for each individual charge. Now, the first one, of course, we start out that's for free. Because let's say, the other charges are infinite distance away. So bringing that one charge here doesn't cost us anything. Say there's no gravity field, this is a massless charge. But then when I bring in another charge, then I have to worry about, or at least have to know, what is the force as a result of this charge being present in the distribution. So when I bring this next charge in, I have to take that into account. So the work for this is not free. I have to take into account the electric field surrounding the red dot, the red charge. And likewise, the next one that I bring in, I have to account for the electric field's superposition of the forces of the previous two charges that are already there. And the next as well. And each one, it becomes more and more complex, and, in terms of determining what is the work done to bring in the next charge. And likewise, more and more. So it's, there's some, I guess, the work done to move each charge, we must determine the total electrostatic potential energy of the whole system discretely or independently. But the most important thing to remember here, this is a scalar. Remember, in the case we have a dot product, the force dotted into displacement. And so now, the vector part of this just goes away. You don't have to worry about the direction, which makes life a little bit easier. And we'll learn later in this chapter that we're able to extract the electric field from the potential, or not potential energy. We haven't gotten to potential yet. And I had a little too much fun with this as well. So we sum the work done to move each charge and then determine the total electrostatic potential of this symbol. That's basically how it's done. But each time we bring in a new charge, it changes the force field distribution. I mean, that's the next charge. This alters that electric field, the field lines, I guess, associated with the whole distribution. Okay, now I want to introduce the concept of electric potential. So now, I have a big charge Q here. Big charge is capital letters. And in that position P, I'm going to introduce electric, basically I'm going to introduce this other test charge at a distance big R away at point P. Let's call this a Q naught. I think you now probably see the analogy between this and force electric fields and potential energy. So I have to bring this charge, from infinity, like I did in the previous cases. So work has to be done, a little different than before. And that's weird. Okay. And remember, this is the identical relationship that we derived on the previous slides. That the potential energy, by doing this integration from infinity to distance r away from the charge, big Q in this situation, not Q1, but this Q. And this is in units of joules. Now, really, the only difference now, what we want to do is electric potential is the amount of potential energy per unit charge. So what we do here is divide the potential energy by this test charge. And by doing so, the test charge goes away. And we're left with the relationship. It looks somewhat similar to the electric field, except we're missing r squared. So you have r squared because it's basically energy per coulomb in this case, or joules per coulomb. But no one ever calls it. No one ever uses these units. This is identical to volts, named after the great Volta, who did a lot of work on batteries and defining voltage in this case. So give him credit for that. But one thing to point out, and if Q, okay, is greater than 0, then V, the voltage, of course, is greater than 0 everywhere here in space surrounding Q. And in the case of the charge is negative, then the potential is also negative surrounding this charge big Q. Really no surprise there. And if we're at infinity, very far away from this charge, then in this case, the voltage or potential is 0 in this case. And again, this is a scalar, just like that of potential energy. So again, this is like the analogy going from a Coulomb force field to electric field. In this case, is electric potential energy to electric potential. We're just dividing out. We're just doing this per unit charge as opposed to total potential energy.
I have a question.
Oh yeah.
Since it says if the distance is infinity, that's when voltage equals 0. Does that mean in reality the voltage is never really 0 in real instances?
Well, real instances, but I mean, if you're in some universe where this is the only charge, let's say magically, magic is probably a bad word, but just somewhere in space, so like interstellar space, maybe within like hundreds of kilometers, perhaps, this could be the only net charge. Probably, I don't know, even interstellar, it's probably intergalactic. I think the density is low enough where that's possible. But yeah, I mean, that's here on Earth, that would be difficult to do. Just that, we live like in a condensed matter universe on the on Earth, where it is in space, it's a different story. I think even the way I described it, you would have to be an intergalactic medium, something like that to be possible.
Well, I think the question was more just theoretical, like just theoretically speaking, as opposed to like in real life.
Well, I mean, think about it. If I have, if I was, wanting to measure the potential, let's say from here to Trabant, that's, I don't know, probably 100 meters or so, compared to that like at 10 centimeters apart. And, we're talking about maybe 3 or 4, yeah, but at least 3 orders of magnitude. So in this case, the potential, let's say here, is at 1 volt. And at Trabant, that would be at, say, 1 times 10 to the minus 3, so like a millivolt, maybe. And if we were to take that further, let's say all the way to Philadelphia, it would be maybe 4 more magnitudes, an order of magnitude smaller. So, but then again, there's so many other charges moving around, and just in the air for that matter. So, I guess, just for, theoretical, or at least, for describing this concept, it's, I think it's perfectly fine, but practicality, I guess you're right, this would be kind of difficult to set up, do an experiment with this. So yeah, yes and no. On Earth, I think this will be difficult. In space, maybe not so much. I don't know if I answered the question or not. All right, moving on. So now, what I think we should look at, say we know in the Van de Graaff, there's charges basically are moved by this pulley, and they're accumulated on this dome. And this, for most part, the dome is spherical. So let's assume that it is for now. And it has like a radius r. And we put some charge onto this dome. And one thing to note, since this is a conductor, it will just spread out uniformly on the surface of this sphere. It's something we'll talk in detail later in this chapter. In fact, we'll return back to Gauss's law and explain some of the phenomena associated with that. So the charge is uniformly distributed on the surface. Inside is 0. Now, we talked about that maybe a week ago in the continuous charge part of last chapter. Just from symmetry, and this, from brute force integration, we found that the electric field has to be 0 inside. And we can also now apply Gauss's law to this. If we have like a surface is inside this spherical shell, it will enclose 0 charge because all the charge is on the outside. And it encloses 0 charge, electric field must be 0. Now, for now, let's just consider the potential outside of the shell, outside of the Van de Graaff, some distance, little r away. And recall from this type of symmetry, the electric field is equivalent to all that charge that we put onto the surface of the sphere to be concentrated at the center. Remember, the electric field comes off radially from a surface such as this. And as a result, electric field, it just gives the same result as if all that charge is concentrated at the center of the sphere. Okay. So now, we just want to consider the case for observation points outside of the sphere. And so this is work done divided by this test charge Q naught. So this is the electric field force as we try to move this charge, this test charge, you can say, from infinity to point R, a distance R away from the center of the sphere. And we have to divide by this test charge. And as you remember, electrostatic force divided by the test charge is the electric field. You can see we have this written that we're actually taking the charge at point R and then we're moving it away to infinity. This is equivalent the other way around. For moving the charge from infinity into R, we just have a sign, SIGN, to contend with. And we've already shown earlier that the electric field should follow this form. Again, this is a scalar, meaning that we dotted the electric field into this directional vector dr. And we can plug in some values for this. We know what the charge is, and that was given to us. And so we know what K is. It's 9 times 10 to the 9. So this is the relationship for this given spherical charge, or is it distributed spherically about the surface of the Van de Graaff, which very close to that of a sphere. So now we have a relationship between the potential at point P and the distance away point P is from the center of the sphere. So I thought it might be interesting to evaluate this at a few places. So let's take it at 1 meter away, and then right at the surface R. Big R, so little r is equal to big R, 20 centimeters is what we would use there. And then we want to look inside. We know already the electric field inside is 0, but that doesn't necessarily mean what the potential is. Okay, if we were to plug in this relationship for R at 1 meter, voltage would be very large. 90,000 volts. And if we're right at the surface, it's almost 500,000. Should say this is not unreasonable. Maybe we'll get to that a little later. If not, we will on Friday. Now, not so obvious what to do with this next one. The integration. So we have to do this integration. This does not apply, obviously, if we're inside the sphere, right? Because the electric field we know is 0. So we have to be a little careful here. So we're taking this so-called test charge, just moving the observation point, so we like to look at it, from infinity inside the sphere to half the radius, that being 10 centimeters in this case. How would we do this? Well, you would need to break this up into 2 separate intervals. Since we have 2 different cases. So we want to integrate from the surface to the R over 2 location, and also from infinity to R. I guess you could say really do in order, be infinity to R, and then from R to R over 2. So what about this first integral? What's going to happen to that?
Would it just be 0?
0 because we're inside the.
That's right, it's 0. Well, what about this integral, the second one? Well, actually, it's no different than the one from the previous case for a little r observation point equals the big R at the surface. So in other words, the potential inside everywhere is constant, roughly 500,000 volts. It does not change. The electric field is 0. So if you were to plot this, it would look something like this. Hope you guys are seeing what I'm seeing. I never know for sure that you're seeing these slides. You should see a graph. On the x-axis is this little r, your observation point, and that would be in meters. We have that's the units on the x-axis, and the y-axis is the potential in voltage. You can see we have this nice 1/r relationship outside of the sphere. But once we enter inside the sphere, the potential is constant. As a result, the electric field being 0. The electric field out here goes as 1/r squared. Any questions about this? I feel like I'm bulldozing my way through.
Is this just for the Van de Graaff, and we'll have different voltage equations for different areas?
No, it's the fact that we're assuming the Van de Graaff is spherically shaped. And as long as we're able to do that, this holds. This holds for any spherically shaped conducting object. It could be an insulator as long as we're able, to uniformly distribute the charges on an insulator, such that the field coming off the surface is radially. This does this automatically for a conductor, which we'll explain later in the chapter. But it's just for this geometry, not necessarily for the Van de Graaff. Well, all right. Well, this is a continuation of this. If you were to go back and say, well, that here, it should be a spherical surface at a fixed distance r away that has the same potential. Everywhere on that particular surface, let's say it's some distance, say it's r equals 1 meter away in this case. On that surface, everywhere, it's 90,000 volts. We can take it out a little further, and we have a bigger, spherical surface in that case. And we would have another voltage. Let's say it's like 2 meters. At 2 meters, it would be 45,000. Every point on that surface has the same voltage. This is referred to as an equal potential surface. And kind of gives you an idea here. If I can get this to run, great.
Is that only for a sphere?
No, actually, this would work for a cylinder. Or many point charges, to say you have a dipole. But of course, the surface would have a different geometry. I don't know why this isn't working. It's supposed to show a surface emanating from this, but great. But yeah, in the case, this is kind of interesting too. If what this little simulation should be showing is a surface that has a greater radius than this inner sphere that you see, and everything on that surface, all points on that surface has the same potential. I mean, that would be like an equal potential surface or a spherical symmetry. And interestingly enough, I mean, that's just like the same type of surface you would want to use for a Gaussian surface. I mean, in the case if you had a line charge, you would have equal potential cylinder surfaces. That's it's concentric, in terms of the cylinder, or the line charge. And all these cylinders, they would have different potentials, but all the points on this, each, say for a single cylinder, single radius, all the points on that surface, would have the same potential. So the geometry changes. Now, somewhat, I was just talking somewhat about, the flux. We were talking electric flux. We really concentrated a lot on that. But the way to view this, the flux, is a vector operation that reshapes the surface to match the geometry of the field, right? So think about it, in the case of a sphere and a point charge, the dot product is the same everywhere on there. So it doesn't change that surface. But if you replace a spherical surface around the charge with a cubical surface, a cubical surface, and if you were to look at points that's off the center, or the center of a face, you have 6 faces on a cube. So you're off center, the dot product is no longer 1 in that situation. And what it's doing is basically it's projecting that surface element to face the electric field. So what it's really doing when you're doing this operation, this vector operation, you're reshaping that surface to match the geometry of the electric field. It's just kind of interesting to look at it that way. I mean, there's multiple ways of doing that. Here, this so happens, I don't think there's any coincidence that, an equal potential surface would make a great Gaussian surface. And one of the reasons why we will find is that the electric field is always perpendicular to an equal potential surface. And so no work is done on the charged particle that remains on this surface. You can take it all the way around, remain on that surface, the electric potential will not change, and consequently there's no work done. This is like a cross section, many equal, this is like a same geometry before we have a point charge. And we have these equal potential circles. And these are just cross sections of equal potential spherical surface. If you were to take the cross section of a sphere, you get a circle. And what is shown here in yellow is the equal potential surface. And the electric fields are blue. You can see they're perpendicular everywhere. I'll get into more details as to why. And it can get really complicated if you have large number of charges. But here, this is the case for a dipole where we have a positive charge on the left and a negative on the right. You can see how it's not very complicated, but you can see how it changes the equal potential lines in this case, being that it's a cross section of a surface. And of course, as you get closer to one charge, as you get closer to like the negative charge on the right, it becomes more and more like a point charge type equal line, and so it's beginning to look like you're able to ignore the positive charge because you're far away from that. So it's beginning to look like concentric circles. But as you get further and further away out, of course, then you begin to be influenced. Just the equal potential lines are being influenced by the other charge. You see in this case as well is that the electric field is always perpendicular to the equal potential surface. One would ask, so why do you need these? You get the electric field, you have everything you need, right? Well, sometimes electric fields can be very complicated to measure, and it's just sometimes much easier to just deal with the equal potential surfaces or equal potential lines. It just sometimes makes life a lot easier And later, some of you guys, especially you electrical engineers or computer engineers, you'll run into this many times. Actually, I wanted to do one thing, but actually this will be a good puzzler for you guys, but at least get you started. What is the maximum amount of charge?
Oh, come on, it's 4/2/15.
That's okay. I
Your mic is
know
on.
that. You guys can leave if you want. I mean, this is not.
Oh, that's my bad.
But yeah, thank you for the information. I appreciate it. But what is the maximum amount of charge on a Van de Graaff generator? At least we know what the Van de Graaff generator can make. It can generate. I mean, actually, it's kind of redundant to say this, but how much can it make? You know, based on what we have here, based on the information, based on the radius. Typically, you know, what will happen is that when you reach the breakdown, electric breakdown for like air, in this case, air, it's standard sea level, temperature and pressure, then charge will begin to leak off. And then at that point, whatever additional charge that you put onto this surface, it just goes away. It just breaks down the air around it. What that means basically when you break down a material, it becomes, maybe